Hello friends, this is Deobrat Pramanik and you are watching my channel Physics Friends. Today's topic is solenoid and its magnetic field. Look at the figure. Here we have considered a solenoid of radius small a and carrying current capital I and having small n number of turns per unit length. We are going to find out its magnetic field at an axial point P. For this, let we consider an elementary portion dx of the solenoid. Then this elementary portion will correspond a circular ring of radius a and having corresponding currents ni dx in it. First, we will find the magnetic field produced by this elementary portion of the solenoid at P. For this, look at the figure. Here, a circular ring of radius A carrying current I produces an axial field like this one, mu naught I square by twice a square plus x square to the power 3 by 2. The axial point is at a distance x from the ring center. Using this result, we can say that the magnetic field produced by this elementary portion, which is of the form of a ring, at P would be mu naught ni square dx by twice a square plus x square to the power 3 by 2, as this elementary portion corresponds a current ni dx. Now, to find out the magnetic field at P due to this entire solenoid, we have to integrate over this. But this integration is not so easy. To make the integration easier, we have to transform this variable x to another one. For this, we have redrawn this figure here. Here the same dx is at an angular inclination theta with the axis respect to the point P. As this angle is theta, this angle is also theta, and we have considered dx is at a distance r from P. So this arc length, this small arc length, is nothing but r d theta. But look at this triangle. This is, for this triangle, this arc length is nothing but dx sine theta. So this arc length is equal to dx sine theta is equal to r d theta. So you can write dx sine theta is equal to r d theta, which gives dx as r d theta by sine theta, and we put the value of sine theta, that is sine theta is equal to a by r, we get dx is equal to a d theta by sine square theta. If we replace these dx and sine theta values, we get dv as mu naught ni square a d theta divided by twice r cube sine square theta, where a d theta by sine square theta, this is the term dx, which gives mu naught ni by 2 sine theta d theta. Now the integration is very simple, which becomes variable of only one variable of theta. So the total magnetic field at P would be integration over this term, and the limit of theta is from theta 2 to theta 1. And what about theta 2 and theta 1? Theta 2 and theta 1 is nothing but the angles made by these two ends of the solenoid with the axis at P. After integration, we get mu naught ni by 2 cos theta 2 minus cos theta 1. For a long solenoid, if the solenoid is a long one and the axial point is within the solenoid, then theta 2 will be 0 and theta 1 would be pi. If we put these two values, we get for a long solenoid field within the axis, within the solenoid, as mu naught Ni. Thanks.